welcome to this session. We will be looking into the as we have talked in the last class, we have finished the modeling aspects of osmotic pressure control filtration in a cross flow cell system. Now we will be talking about the importance of unstirred batch system and do things, and then we will be looking into the modeling of unstirred batch filtration system, membrane filtration system. Why the unstirred batch system is important, that has to be understood first, because if we are dealing with a real time with a solution having a solute with known properties, then it is very easy to solve the system using a predictive mode. But suppose we are talking about an industrial effluent or a fruit juice or an unknown or real life application, where there will be not a single component. There are many components present into the system, and it is very difficult to identify each and every component, number one. Number two is that even if you identify every majority of components, then it will be quite difficult to estimate their concentration. Even if you estimate the concentration, now it will be very difficult to estimate their physical property of each and individual material component, for example, their diffusivity, osmotic pressure of the solution, things like that. So, therefore, what is generally done, one has to take an effective diffusivity and effective osmotic pressure with a variation of concentration. Concentration may be in terms of total solids or total dissolved solids based on the system, and you will be having an effective osmotic pressure coefficient A1C plus A2C square plus A3C cube. This A1, A2, A3 may be the the effective coefficients of osmotic pressure. So, let us write down what are the various parameters. Those will be appearing: A1C plus A2C square plus A3C cube, that will be the osmotic pressure of the solution, but we do not know the values of A1, A2, A3. And even if you can know if you have an accurate osmometer, but if you do not know the value of effective diffusivity, effective viscosity, and viscosity can be measured, of course, but the diffusivity value cannot be known. So, it will be, so in a typical system you will be having 4 unknowns: the osmotic coefficients A1, A2, A3 and diffusivity, effective diffusivity of the system. So, how this system is then modeled? Then what is generally done, we conduct large number of experiments, in the order of 30-40 large number of experiments, and vary the operating conditions and see the permeate flux and permeate concentration, and maybe in terms of total solids or maybe in terms of total dissolved solids. Once this is done, then we go through the model, but we have a profile optimization or the optimization with respect to the experimental values. So, we have a guess values, we do a guess values of A1, A2, A3 or D, then we go to the model, solve the model, get the calculated value of permeate flux and permeate concentration for different operating conditions, and then we compare those values with the experimental data. That means, we minimize the sum Cp calculated minus Cp experimental divided by Cp experimental, square of that plus Vw calculated minus Vw experimental by Vw experimental, square of that. We minimize the sum and compare and optimize the whole system and compare with the experimental data and the model calculated data. Then, if this sum is not less than a tolerance value, then again we have to redo a re-guess this set of parameters, which will be directed by a proper algorithm or minimization algorithm or optimization algorithm. So, we will be doing an optimization method, optimization for evaluating the system parameters. So, then A1, A2, A3 and D of the system will be predicted, will be estimated. Once this will be estimated, then for an unknown operating conditions, we can run our model equations in a predictive mode in order to predict the system performance. So, what is the drawback of the system? If you really do a cross flow system, then every cross flow system will be under a particular set of operating condition will be giving you one value of permeate concentration and permeate flux, but you require probably huge number of experiments. So, therefore, you have to conduct the cross flow experiment large number of times, maybe 40 times 50 times, in order to generate 40-50 values of permeate concentration and permeate flux, and so that you can optimize the 4 parameters A1 to A3 and D effective. Now, that will be incurring, then you will be incurring more cost, manpower, energy, and material to conduct those experiments. On the other hand, if you can conduct a batch cell experiment, the permeate in a typical batch cell, because of the growth of the mass transfer boundary layer, one will be getting the permeate flux and permeate concentration profile of that as a function of time. So, you will be getting the n number of data. So, these will be the parameters, and this will be function of time. The permeate flux will keep on decreasing as a function of time. This will be the permeate flux Pw, the non-dimensional permeate flux, and this is how the permeate concentration, non-dimensional permeate concentration keep on growing as a function of time. So, what you can do at any fixed time intervals, you can measure the permeate concentration and permeate flux. So, you can keep on measuring them. You conduct an experiments for 5 hours, one single experiments for 5 hours, and then you can measure n number of values of permeate concentration and pair of permeate concentration and permeate flux at different time points. So, therefore, if from a single experiment one can generate data 50-60 data if you take a run of, let us say, 2 hours or 3 hours, and if you take data accurately within every 10 minutes or 5 minutes. So, depending on the duration of the experiment, one can collect large number of data, and those data can be minimized by doing an optimization. So, that is known as the profile optimization. So, you have the model value of permeate flux profile and model value of calculated value of permeate concentration profile. You measure the experimental values and plot the experimental values like this. And from a single experiment, single batch cell experiment, one can get a large number of data. That is why the modeling of the batch cell filtration setup is very important, and we will be looking into how this modeling can be done. So, for an actual real system, the rigor of experiment can be reduced, or in order to estimate the parameters quite easily from the batch cell experiment. So, let us look into the modeling of the batch cell experiment. What is a batch cell? So, it is basically a pressure vessel having 3 parts. There will be a top flange, there will be a body or shell, there will be a bottom flange, and this in the bottom flange it will be a circular disc. So, here you will be placing the membrane, and in the top flange, and all these will be connected to the filtration body of the cell by using nuts and bolts, and then it will be pressurized by a nitrogen cylinder. But before that, you fill up the cell with, let us say, 500 ml or 700 ml of solution. So, what will be, let us write down. So, there will be a growth of concentration boundary layer over the membrane surface, as we have seen earlier, but in this case there is a difference. The difference is that in the case of the cross flow filtration, the growth of the mass transfer boundary layer will be restricted or arrested by the cross flow of the retented flow. But in this case, so there will be a steady state reached in case of the cross flow filtration, but in the case of unstirred batch cell, there is no external agent to curb or arrest the growth of the boundary layer. Hence, it will be growing undisturbed, and the permeate flux will keep on decreasing as a function of time, and permeate concentration will keep on increasing as a function of time. So, there will be no attainment of steady state, that is the unlike the cross flow filtration cell, that is the typical characteristic of a batch cell. No attainment of the steady state. So, thus what we will do next, we will write down the solute mass balance. within mass transfer boundary layer. So, if you write it del C del T minus plus V del C del Y is equal to d del square C del Y square. Since mass transfer boundary layer is small, we can assume V is equal to minus V W. So, that is coming out, and in this case V W will be function of time. So, del C del T will be minus V W del C del Y is equal to d del square C del Y square. So, now let us set the set up the boundary conditions at t is equal to 0, C is equal to C naught, at y is equal to infinity as argued earlier, C is equal to C naught, at y is equal to 0 we have all the pseudo steady state boundary condition, all the mass fluxes towards membrane surface will be equal to 0. So, V W C m minus C P plus d del C del Y will be equal to 0. So, this will set up the governing equation and the 3 boundary conditions. Next, what we will do? We make the system non-dimensional from the very beginning. So, let us do that. So, we define these non-dimensional parameters as C star is equal to C by C naught, Y star is equal to Y by R. R is the radius of the batch cell. So, now let us look into the governing equation. So, this becomes del C star del T minus V W del C star R del Y star and d del square C star divided by R square del Y star square, okay, multiplied by R square by d. So, it becomes R square by d del C star del T minus V W R over T del C star del Y star is equal to del square C star del Y star square. So, the right hand side is completely non-dimensional, the second term in the left hand side this is non-dimensional. So, this is again non-dimensional permeate flux in this case. So, here C star is non-dimensional, T is dimensional, that means T d by R square has to be non-dimensional. So, that means we define non-dimensional time as T d divided by R square. So, this becomes del C star del tau minus P W del C star del Y star is equal to del square C star del Y star square. So, this is the governing equation where P W is equal to V W R over d. Okay. And now, we will be making the boundary conditions to be non-dimensional as well. So, at tau is equal to 0, C star is equal to 1, at Y star is equal to 0, del C star del Y star plus P W C m star R r equal to 0, at Y star is equal to infinity, C star is equal to 1. So, that sets up the governing equation and the boundary condition. So, next again we will be taking recourse to the similarity solution, because this is a parabolic partial differential equation and one of the boundary is residing at infinity. So, we can have a similarity solution. So, let us have a similarity solution, and before that we have to find out what is the similarity parameter. So, again we will be doing the same order of magnitude by evaluating this concentration profile at the edge of the boundary layer. So, this will be, if we really do that, del C star will be delta C star and delta tau will be tau minus 0, the second term will be gone. So, that will be delta C star divided by delta square. So, delta square will be function will be varying as under root over tau in this case. So, now we will be getting a similarity parameter. Similarity parameter is Y star by del star and it will be Y star by root over tau. So, that will be the similarity parameter we will be working with in this particular problem. Next, as we have done earlier, we will be replacing all the partial derivative in the governing equation in terms of the similarity parameter, and let us first find out the partial derivative of those will be appearing in the governing equation in terms of the similarity parameter. Once we get those expressions, we are going to substitute those expressions in the governing equation. So, del C star del tau will be nothing but d C star d eta del eta del tau, and this becomes minus 1 by 2 y star tau root tau d C star d eta, and y star by root tau is nothing but eta. This is nothing but eta by 2 d C star d eta. Then del C star del y star becomes d C star d eta del eta del y star, and this becomes 1 over root over tau d C star d eta, and del square C star del y star square is del y star del C star del y star, and this becomes 1 over tau d square C star d eta square. So, now we are going to substitute these partial derivatives in the governing equation and see what we get. So, what we get is that d square C star d eta square is equal to minus eta by 2 plus V w root over tau d C star d eta, and as we have already seen that the delta V w is inversely proportional to the delta. So, this will be P w, right. P w is inversely proportional to delta star, and delta star is directly proportional to root over tau. Therefore, P w root over tau is constant, and this constant, let us say this is A. If that is the case, then the ordinary differential equation of second order now becomes minus eta by 2 plus A d C star d eta, and now we change the boundary conditions in terms of similarity parameter eta equal to 0 d C star d eta plus A C m star r r equal to 0, and at eta equal to infinity C star is equal to 1. So, now we will be able to solve this equation. So, d C star, so solution is as we have seen earlier, d C star d eta is equal to k 1 exponential minus eta square by 4 minus a eta, and then one more integration will be giving you C star as a function of eta k 1 exponential minus eta square by 4 minus a eta d eta plus k 2, and then using the boundary conditions, these two boundary conditions, one can evaluate the integration constants k 1 and k 2 as k 1 plus a r r k 2 is equal to 0, and k 1 I 1 plus k 2 is equal to 1. So, where I 1 is basically the definite integral 0 to infinity p exponential minus eta square by 4 minus a eta d eta, okay, and k 1 becomes minus a r r 1 minus a r r I 1, and k 2 is nothing but C m star is equal to 1 over 1 minus a r r I 1, and we have the osmotic pressure model. So, Darcy's law to the porous medium, porous membrane, P w as a function of time will be nothing but B into 1 minus delta pi by delta p, and we have already seen that delta pi can be expressed as a function of Cm star. So, now the model equations complete. Let us look into the algorithm of calculation. The algorithmic calculation is very simple. First, at a particular time point tau, we do following: 1, guess Cm star, evaluate P w from equation 1, once you get PMW from equation 1, then you can get the expression of A from expression of A can be evaluated from expression of PW. Okay. Once that is done, then you can evaluate I1 from equation 2. Once that is done, one can evaluate Cm star from equation 3. Okay. So, therefore, the expression of P w is nothing but A is equal to P w root over tau. So, A is equal to P w root over tau. So, at that particular tau we put the value of tau. We have already evaluated P w. So, P w multiplied root over tau will be giving you the value of A. Substitute A in integral I1 and evaluate the definite integral using trapezoidal rule and get the value of I1 from equation 2, and from equation 3 you will be getting the value of Cm star, and check whether this calculated Cm star, now Cm star calculated minus Cm star guess, they are less than epsilon or not. If they are less than epsilon, then you go for the next time step t plus delta t. If not, then you have to re-guess the value of Cm star and repeat the iterative calculation. So, in the process what you will be getting is that in the process you will be ultimately getting Cm star as a function of time, Cp star as a function of time, and Pw as a function of time. So, ultimately you will be getting Pw as a function of time and Cp star as a function of time, and you will be having the measured value of Pw at different time points and measured value of Cp star different time points. Then you can do the optimization and can estimate the system parameters. So, that is how the the batch cell filtration can be done. So, this completes our whole formulation for the modeling or content for the modeling of the osmotic pressure filtration, both in the cross flow cell and the batch cell. From one dimensional model, we first started with the one dimensional model, we went ahead with the two dimensional model, and by observing several shortcomings of the one dimensional model, and we have seen that one dimensional model will really give the under prediction of permeate flux, and therefore, we went ahead with the two dimensional model, completely solved the two dimensional model for the cross flow filtration system as well as the batch system filtration system. Also, we have iterated that discussed about the importance of the batch cell, why it is so important for evaluating the system parameters or the process parameters whenever you will be working with a real industrial fluid or a real fluid sample. Next type of modeling will be looking into the gel layer control modeling. Under two circumstances, a gel or highly viscous solution is prepared on the membrane is formed on the membrane surface. There are two ways. First way is that the filtration may be osmotic pressure controlled initially, and then during the osmotic pressure control filtration, membrane surface solute concentration on the membrane surface keep on increasing as you move downstream of the channel, and therefore, at a particular location it may happen that it exceeds the solubility limit, exceeds or approaches the solubility limit. In that case, once it does that, then a very viscous solution is formed near membrane surface, and if the solubility limit is exceeded at that particular temperature, there may be precipitation of the solute as a solid phase, or there may be another way is a natural gel forming agents. There are some natural gel forming agents. For example, polyvinyl alcohol, pectin, etc. These solutes, they form a gel over the membrane surface from the very beginning. So, you do not need to give time for them for formation of the gel, they already form, from the very beginning of the filtration, they form a solid gel type of, they form a highly viscous solution, highly viscous layer near the membrane surface, and this gel keeps on growing in time with the time of operation or duration of operation in the y direction over the membrane surface. So, there are two typical ways how the gel is formed, and in the next class we will be looking into the various types of gel polarization model, and how the various parameters will be estimated in a typical gel polarization model, which will be basically will be taking cue from the classical filtration theory and combine it, and we will bring those concepts in the gel layer formation, and then we will be looking into the how the gel layer modeling can be done. Thank you very much.